The conflict in Ukraine, the Black Sea, and the Persian Gulf, and rising tensions across global waterways have sparked intense debates regarding the future of naval warfare. One key question dominates this discourse. Has the dominance of large, crude warships come to an end, increasingly replaced by cheap drone swarms? The answer requires a rigorous separation of capability from hype. The narrative that small drones can easily defeat traditional fleets ignores the fundamental constraints of geography and the challenges involved in long-range communications. Autonomous systems are indeed transforming naval operations, but their impact varies drastically depending on the environment. To evaluate their true utility, we must look at the four distinct families of naval drones dominating naval procurement programs: unmanned surface vessels, one-way attack aerial drones, high-altitude and medium-altitude long-endurance unmanned aircraft, and uncrewed underwater vehicles. Each category possesses unique strengths and severe limitations. Understanding where these technologies succeed and where they fail is critical to predicting how drones will actually impact naval warfare over time. Unmanned surface vessels, or USVs, represents the most combat-proven application of unmanned naval technology. These platforms are essentially low-profile, uncrewed speedboats packed with explosives, designed to function as steerable projectiles running on the surface. They utilize low radar cross-sections, highly efficient commercial-grade hull forms, and sophisticated satellite communication links to traverse hundreds of kilometers. Upon reaching the objective area, they exploit darkness or numbers to approach and detonate against the hulls of enemy vessels. The most prominent examples of this technology have emerged from the Black Sea, where the Ukrainian military has extensively deployed the Magura V5 and the Sea Baby USVs. These platforms have fundamentally impacted the naval balance in the Black Sea through damaging or sinking a range of Russian warships, including the Taranto-class missile corvette, the Rapucha-class large landing ships, and even putting out of action the Admiral Grigorovich-class frigate. By operating in swarms, utilizing multi-mode optical sensors, and exploiting the vulnerabilities of anchored or poorly defended warships, Ukrainian forces have forced the Russian Navy Black Sea Fleet to disperse its warships from its historic headquarters at Sevastopol and retreat to more distant ports away from the Ukrainian drone threat emanating from Odessa. The strategic efficacy of one-way attack surface craft is highly dependent on the geography of the maritime theater. These assets excel in confined, shallow, and littoral environments. In these narrow waterways, large warships lack the space to maneuver freely and are constantly exposed to shore-based tracking system. The Black Sea campaign demonstrated that a determined adversary utilizing dozens of low-cost USVs can achieve catastrophic results against traditional surface units, inflicting heavy damage on modern frigates, landing ships, and corvettes. A similar dynamic has emerged in other critical choke points. The United States Navy recently expanded the operational scope of surface drones during strikes against Iranian maritime infrastructure. US Central Command deployed the Saronic Corsair USV, a 7.3-meter autonomous watercraft with a top speed exceeding 35 knots, to strike a submarine and ship maintenance facility at the Bandar Abbas naval base of Iran. The operation targeted anchored assets, including a Gardner-class midget submarine, proving that USVs can project offensive power without risking human personnel. In narrow maritime theaters like the Red Sea, the Persian Gulf, and the Taiwan Strait, the threat posed by such systems is real, forcing naval commanders to treat coastal waters as high-risk zones. Despite these notable achievements, one-way surface drones suffer from significant limitations that prevents them from displacing traditional surface fleets in a blue water environment. The primary constraint is the combat range in a blue water context. While a USV might possess the theoretical endurance to travel over 1,000 kilometers at an economical cruising speed, its tactical utility decreases the longer it remains at sea. Long transits across open waters increase the probability of detection by aerial reconnaissance, radar picket, and satellite surveillance. The shorter the distance from the launch point to the target, the easier it is for an operator to achieve the elements of surprise. Surprise is absolutely vital to the success of a USV attack. If a warship detects an incoming surface craft at a reasonable distance, the drone faces an incredibly high probability of destruction. The speed of the target also matters. A static target, such as a Russian or Iranian warship moored at a pier, presents a straightforward objective. A carrier strike group moving at 30 knots in open water presents an entirely different problem. In open ocean settings, where naval engagements occur at extreme ranges via anti-ship cruise missiles and carrier-based aircraft, a slow-moving, surface-bound drone will simply never close the distance to its target before it is discovered and quickly destroyed. The physical realities of the maritime environment imposes another severe restriction on unmanned surface vessels. This is the impact of volatile sea states. In the open ocean, weather conditions dictate tactical utility for low freeboard vessels. A high sea state featuring high waves is a minor nuisance to a 9,000-ton class destroyer, which is designed to maintain high speeds and fight effectively through heavy weather. For a small, low-profile USV weighing only a few tons, the same waves present a formidable barrier. Because these craft rely on low freeboard to maintain a minimal radar signature, they're easily swamped, flipped, or structurally damaged by rough waters. High waves also degrade their optical sensors, breaking their line-of-sight communication links, and sap their limited fuel or battery reserves as they struggle against intense hydrodynamic resistance. In many cases, turbulent seas may cause the outright loss of a USV before it can even approach a target. This vulnerability reinforces the argument that surface drones are fundamentally poorly suited for blue water environments, where open ocean weather is unpredictable and volatile sea states can render an entire drone swarm ineffective. A parallel evolution has occurred with one-way attack aerial drones, often referred to as loitering munitions or kamikaze drones. These platforms offer an airborne equivalent to the explosive USV. The most widely recognized system in this class is the Iranian-origin Shahed 136 system, along with its numerous variants, such as the Russian Garan 2 family. These aircraft utilize simple delta-wing designs, loud but efficient basic engines, and satellite navigation systems to fly predetermined routes towards fixed coordinates or naval targets. Recognizing the utility of low-cost aviation in contested environments, the US military has pursued its own programs, including the low-cost uncrewed combat attack system, or LUCAS, which serves as an American equivalent designed to saturate enemy air defenses at a fraction of the cost of a cruise missile. Like their surface counterparts, one-way attack aerial drones are highly effective when deployed within confined littoral environments. Russian forces have frequently utilized the Shahed and the derivative Garan attack drones to target Ukrainian port infrastructure along the Black Sea coast, striking grain terminals, loading docks, and large vessels. In narrow waters like the Red Sea or the Taiwan Strait, a massed volley of these low-flying, slow-moving aerial systems, or something equivalent, can present a severe challenge to commercial and military vessels alike, forcing defending forces to expand ammunition and radar tracking capacity. However, the limitations of one-way aerial drones mirror those of surface variants. Their range is structurally constrained by fuel capacity and the aerodynamic compromises required to keep unit cost low. Furthermore, achieving the surprise necessary to bypass a modern integrated air defense system becomes exceedingly difficult over long distances. Unlike USVs, which exploit the radar clutter of waves and coastal terrain, an aerial drone flying through the sky is highly visible to modern air search radars and airborne early warning planes. Naval defenses against airborne threats are much more mature and sophisticated than defenses against surface skimming watercraft. Most modern warships feature layered air defense systems, including close-in weapon systems like the Phalanx or the Goalkeeper, alongside short-range surface-to-air missile systems like the Rolling Airframe Missile. The option to use longer-range air defense missiles is also there. While expanding a multi-million-dollar medium-range air defense missile to intercept a cheap aerial drone is not financially sustainable over a long campaign, that option remains available to many warships if the need arises. And saving a warship is worth the cost of an expensive missile. In a high-end blue water fight, one-way attack aerial drones lack the speed, survivability, and range to really threaten a modern navy. To project uncrewed power into the deep ocean, militaries must turn to a completely different class of technology: high-altitude, long-endurance, and medium-altitude, long-endurance platforms, collectively referred to as HALE and MALE drones. These are large, sophisticated, and expensive unmanned aircraft designed to stay airborne for fairly long periods at substantial altitudes. Well-known examples include the American MQ-4C Triton, the Turkish Bayraktar TB3, and Chinese designs such as the WZ-8 reconnaissance drone and the GJ-11 and GJ-21 stealthy strike platforms. These systems can operate from land bases, or in the case of platforms like the Bayraktar TB3 or the GJ-21, deploy from the decks of aircraft carriers and amphibious assault ships. In the vast expanses of the open ocean, the primary function of these large drones is not usually direct attack, but rather wide-area maritime reconnaissance, persistent surveillance, target acquisition, and electronic warfare. By acting as high-altitude sensor nodes, they feed real-time tracking data to crewed warships, extending the eyes of the fleet far beyond the horizon. Certain advanced variants, like the stealthy GJ-11, are also configured to carry precision-guided anti-ship munitions, allowing them to perform standalone strikes against surface targets. While these large, long-endurance drones are far more relevant to blue water naval warfare than one-way attack systems, they do not offer a cheap shortcut to maritime dominance. These aircraft are massive, complex machines packed with expensive systems of all kinds, like synthetic aperture radars, for example. Consequently, their unit costs are comparable to and sometimes exceed those of crewed fighter jets. They are more expendable than a crewed aircraft, only in the sense that their destruction does not result in the death of a pilot. Because they are expensive, sophisticated, and produced in small numbers, they cannot be deployed in disposable swarms. A peer adversary possessing long-range air defense destroyers, such as the US Navy Arleigh Burke class or the Chinese Type 055 class, can detect and track these large drones using standard long-range surface-to-air missiles. High-altitude, long-endurance, and medium-altitude, long-endurance drones are highly vulnerable in contested airspace. They are designed to complement the existing capabilities of a crewed naval task force, serving as force multipliers rather than standalone replacements for traditional warships. The final frontier of naval drones exists beneath the surface, where uncrewed underwater vehicles, or UUVs, operate. These systems fall into two broad categories: small one-way attack underwater drones and large multi-role UUVs. A one-way attack UUV functions essentially as an autonomous long-range torpedo, designed to transit beneath the waves before detonating against the vulnerable keel or propeller of a ship. Conversely, a large UUV is a true uncrewed submarine, capable of executing diverse, complex operations over extended periods. Notable examples of large underwater drones include the US Navy Orca extra-large UUV, the Chinese HSU-001 autonomous underwater vehicle, and Ukraine's recent entry into the field, the Sea Trident ST-1000. Unveiled by the Ukrainian defense firm Global Mark, the Sea Trident is a 10-meter-long, 10-ton underwater craft able to dive to depths of 60 meters. It possesses an operational range of 2,000 nautical miles, a cruising speed of 6 knots, and can carry a massive 1,000-kilogram warhead or payload. The use cases for these systems are highly specialized, focusing on mine countermeasures, anti-submarine warfare, and covert penetration of ports. Large UUVs act as expendable sonar pickets, clear minefields, track hostile submarines, or potentially deploy their own torpedoes against enemy vessels. Small one-way UUVs suffer from severe physical constraints that restrict their utility outside near-seas operations. Traveling through water requires vastly more energy than flying through the air or skimming across the surface due to hydrodynamic drag. To preserve battery life and achieve any meaningful range, an underwater drone must travel at a painstakingly slow speed, typically between 3 and 6 knots. Even if the drone can make a high-speed dash during its terminal attack phase, its slow transit speed makes intercepting a moving warship nearly impossible. To circumvent this limitation, the Chinese defense industry has experimented with a novel deployment idea, using a large aerial drone to airlift a small UUV directly into the combat zone. Once an enemy submarine is detected or suspected by broad area sensors, the aerial drone drops the UUV into the water nearby, allowing the underwater system to utilize its limited energy reserves exclusively for hunting the submarine target. Larger UUV systems, like the Sea Trident ST-1000 or the American Orca, feature much greater range and capacity for sustained speed. Yet, they remain shackled by the physics of underwater communication. Seawater is essentially impassable to high-bandwidth radio waves. A UUV operating deep underwater cannot receive real-time updates or orders from a human commander. To communicate, the vehicle must slow down, rise to the surface, or extend a vulnerable antenna above the waterline, immediately exposing its position to radar and visual detection. Alternatively, it must remain static and wait until it passes directly over a pre-installed acoustic data node anchored to the seafloor. This communication lag means that if the tactical situation shifts rapidly on the surface, a UUV cannot adapt on the fly. It lacks the flexibility of an aerial drone or a surface craft connected via satellite link. This communication isolation creates a key challenge relating to the identification friend or foe, or IFF. An autonomous underwater vehicle lacks the human judgment, contextual awareness, and real-time communication necessary to verify a target's identity before deploying lethal force. A UUV relies entirely on its passive sonar arrays to listen for contact, or its active sonar to pin the surrounding environment. However, acoustic signatures are notoriously ambiguous. The ocean is filled with acoustic noise, and an algorithm running on a UUV must attempt to distinguish the sound of an enemy submarine from a friendly vessel, or indeed from a commercial ship, or biological anomaly like whales. If the drone makes a mistake, the consequences are severe, ranging from the sinking of an allied or friendly warship, or even a neutral ship, potentially triggering an international crisis. Because the technical risks surrounding IFF are so high, weaponizing large UUVs with torpedoes for direct autonomous combat against surface ships remains a highly dangerous proposition. Consequently, modern naval planners view large UUVs primarily as tools for non-lethal or indirect missions, utilizing them for mine clearance and mapping of the underwater geography, for example. The critical takeaway for naval analysts is that the impact of uncrewed systems depends entirely on geography and operational context. Drones are undeniably effective in confined coastal waters. In regions like the Black Sea, the Red Sea, and the Persian Gulf, where ranges are short, communication links are stable, and the elements of surprise is achievable, low-cost unmanned platforms pose a severe asymmetric threat to traditional naval power. These unmanned systems have not rendered the crewed warship obsolete, but they have altered the cost-benefit equation of operating close to the shoreline of an adversary. Modern surface ships must adapt, integrate comprehensive anti-drone capabilities, short-range guns, and electronic jamming systems into their baseline designs to survive in the coastal zone. In the vast, unyielding environment of open ocean, blue water warfare, the drone revolution appears entirely different. The fundamental challenges of extreme range, harsh maritime environments, and sophisticated air defenses neutralize the effectiveness of cheap, short-range, one-way attack craft. In the middle of the Pacific Ocean, a fleet cannot be defeated by a swarm of explosive motorboats or slow-moving, loitering munitions. In this arena, large, expensive, long-range drones and long-endurance UUVs are the only viable unmanned platforms. These systems do not replace the traditional fleet, they serve it. They function as eyes, ears, and extended sensors, operating in deep integration with crewed destroyers, submarines, and aircraft carriers. By separating capability from hype, it becomes clear that naval drones are not a silver bullet destined to sweep traditional navies and traditional manned warships from the seas. Instead, they are a powerful set of tools that will complement and extend rather than to replace the reach of crewed naval vessels.